So, first of all, the problem is n equals 1 of this. I'm just writing the equation real quick. Excuse the background noise, I'm out right now. Converges to S. So what is the least number of terms in a series that must be summed to guarantee a partial sum within 0.001 of S? So step 1, alternating series. So we know that 1, negative 1 n makes an alternating series. For alternating series to converge, the terms need to get smaller, and they need to approach 0. So go to 0, which does happen at p of 1. Step 2, absolute convergence. So now we can ignore the negative 1, and we have to see if the series converges at. Well, let me just rewrite the equation. To see if it converges there, and it behaves like sigma of n equals 1 of n1 minus p, which we know is a p series. So it would be 1p negative 1. So it only converges there. P 1, but not absolutely. So step 3, conditional convergence, meaning when the series converges, but not absolutely. Not absolutely. So, converges when P1, that's a greater than, sorry, but converges absolutely when P equals 2. Well, no, P is greater than 2, sorry. So, the answer would be, when is it conditionally convergent? And it would be C, which is 1 of P negative 2 only. I actually wrote the wrong this here. I wrote that wrong. I meant to write the n equals 1, infinity of negative 1, and I don't know how I wrote the wrong one. So I get confused. So, 1 convergent. And then at C. Okay. The next problem, which is problem 6, is integral test can be used to determine that which of the following statements is true about infinite series. And it's the one they gave us, which is infinity n equals 1, e is 1 over n squared is. So that's it there. So step 1, we have to use the integral test. Sorry, I wrote that wrong. We have to use the integral test. So at sigma of 1 infinity e to the 1 over n squared. The test ends up linking to, sorry, my handwriting's really bad, to the convergence of the series. To converge of the related integral, it links to each other, and it just ends up going like that. So the integral is, we define the integral by evaluating infinity. Sorry, trying to think of it as I'm writing. And I think, okay. Whew, it's hard to multitask and explain. So yeah, we have to evaluate the integral, and the next, so that was step 2, I have to write that. Step 2. Now step 3, we have to substitute. So let u equal 1 over x, and for du equal negative dx of x squared. So the integral ends up becoming 1 e d negative du, right? And then you have to write like this, what you substituted for. So 1 to 0 of e u du equals e to 0 with that. So ends up equaling, after substituting, e minus 1. So then after that, we have to, because we're not done yet, convergence. So, oops, I assume it's eraser. The integral converges to the finite value, which is e minus 1. So ends up giving us, this test ends up telling us that the original series, which was e to the n equals 1, infinity, okay, that's weird. Also converges. So that would be making A, option choice A, which was right over here. Series converges because infinity 1 over x, which is A. So that's for question 8. 6, I meant to read 6, sorry. I was thinking of correcting question 8, but it's question 6, and the answer is A. So, last problem I'm going to be doing is question 10. And this is the equation. The series, infinity, I'm going to make this brush smaller. I also switched brushes because in my other parts, the brush was not that well. It was making stuff look way less. What's the word? Way less readable. So, the series of the sigma infinity to 1, and the negative 1 n plus 1 over 2n minus 1, and that special mark, it converges to S. And based on that, the alternating series is the series error bound. What is the least number of terms in the series that must be summed to guarantee the partial sum that is within 0.001 of S? So, start off. Step 1 would be, I think, alternating series. Oh yeah, we use the alternating series estimation theorem. So the error in the sum of the alternating series by its first nth term less than the absolute value of the next term. So first n term, sorry, I'm trying to make this legible, but I'm really struggling. I'm using an Apple pen because honestly, it's not bigger. The first n term less than absolute value of the next. So step 2, we would have to know where the error bound is, and that is when the error bound is going to be less than 0.001, which it says in the top up here, less than 0.001. So we have to find the smallest n, which would be bound by 2n plus 1. That's exclamation mark thing. 0.001. So that would prove that by finding the smallest n. And then for step 3, we have to, from that, I'm trying to think. Solve the inequality. I'm trying to write it out, but I'm trying to write it out while it's still making sense. But thinking at the same time, because I'm writing it. Okay. So the inequality is equivalent to 2n plus 1, the special sign of 1,000. So after that part, you have to finally test the values. So step 4. And we know that I'm kind of testing out, but I already using this, so n equals, that'll be the first one, and then I'm trying to think of it, solve it at the same time. Okay. So found that one. We're just testing the values. Well, no wait, why was I only going to use I'm just testing the values. And then equal, yep. So we got 6, 120, and then 5,040. So lastly, since 7 greater than 1,000, oops, it's a eraser, sorry, greater than 1,000, we would still need the last 3 terms. So n equals 3, which was, let me look at the problem again, which that would make the answer. The correct option would be option B, which was 3. Honestly, when I was doing these on the test, I couldn't understand it correctly, but after looking back and I reviewed my notes, I kind of understood a little bit better. But it's kind of hard to think of it and then say it out loud at the same time. But yeah, here's my test corrections. I hope they weren't that bad. I tried my best. Also, I love our potlucks that we have in class, especially one from Pi Day. This is a pie if you can't tell. Yay. But anyways, thank you. Have a good day or night or I don't know, whatever time you're gonna be watching this.